Okay, today's lesson is solving problems using trigonometry. Learning goal is after this lesson we can use trig to solve 3D problems involving right and non-right angle triangles. So our three main components of trig we've learned so far would be the cosine law, the sine law, and SOHCAHTOA. And all of those we want to be able to solve for side lengths in triangles, and we want to be able to solve for angles in triangles. So we know solving side lengths generally slightly easier, one less step. When we solve for angles, we have to use the inverse functions. And that looks like cosine inverse on your calculator, or tan inverse on your calculator, and of course sine inverse on your calculator. If you know how to solve for both sides and angles using cosine law, sine law, and SOHCAHTOA, you have figured out a lot of the trig we've done so far. You'll be in good shape. So on your lesson package, you don't have this extra diagram to the right. I threw in an extra diagram because it's a little confusing, that image on the left-hand side. But the point they're trying to get across is there's a cliff, and we're trying to measure the height of this cliff. So from A to B is the height of the cliff. I'll label that H right there. And then there's some sort of river or triangle on a horizontal plane at the base of the cliff. So B, C, D is on a different plane. It's on a horizontal plane. It's flat along the ground, where triangle ABC is on a vertical plane. So while they share a common side BC, they do not share any common angles. This 39-degree angle here has nothing to do with this 69-degree angle here. They are independent of each other. I'll fill in my missing values, 47 degrees and 143. So the way we're going to tackle this problem is solve for the horizontal triangle BCD, and we want to solve for what is common. So we want to solve for side BC in triangle BCD because it's common in both triangles. Then we're going to use that knowledge to solve for H in triangle ABC. So if I redraw this triangle, it's usually a good idea to redraw a triangle just to get a clear understanding of what's going on from the diagram. BDC, got an angle here we know, got an angle here we know, and we know the bottom 143. So taking a look at this triangle here, if that was all that was given to you, you didn't have to do anything else, it would be relatively easy to solve. We could say, okay, well, we want a complete ratio, so I'm going to solve for angle B up here in the top. Angle B is going to be 180 degrees minus 69 minus 47, and we've got 64 degrees there. 64 degrees. Then, instead of using cosine law, we realize we can use sine law here because we have a complete ratio. We have angle B and side length B. Then we want to compare it to this ratio of angle D and side length D is what we're looking for. So to solve for side length D, we're going to use sine law. It's going to be D over sine D is equal to B over sine B. So D is our unknown. It's in the numerator. That's nice. Over sine of 47 degrees is equal to B 143 over the sine of angle B, which is 64 degrees. So we've got 143 times sine 47 divided by sine 64. Once again, I just multiplied onto the top. If you're unsure what I did in that step, go back and watch the sine law video. Then multiplying those out, we get 116.36. Some calculator work. Make sure you can get that on your calculator. Is side D or side length BC. We might want to call that BC because we're going to have it in common with the next triangle. So if I look at the next triangle, our top triangle, I'm going to draw it in 2 dimensions so we get a real grasp that that has a 90-degree angle in it, because from the first diagram it doesn't overly look like 90 degrees there, but we have to realize it's on a vertical plane. It's hard to draw a triangle on a vertical plane on a two-dimensional piece of paper. So for angle ABC is a right angle triangle. We have 39 degrees down there, and we just solve for this side length being 116.36 meters. And of course we want to solve for height. So if I just gave you this triangle and ignore the rest of it, it'd be a pretty simple process to solve. We need to solve for the opposite, knowing the adjacent. So what trig ratio uses opposite and adjacent? TOA. So tan theta, or in this case 39 degrees, is equal to opposite, which happens to be h, over BC, which happens to be 116.36 meters. I'm going to leave out the meters there actually. So multiply both sides by 116.36 to get that out of the denominator, and we get 116.36 times the tan of 39 degrees is equal to the height of the cliff. Then that's some calculator work. Make sure your calculator is in degrees. You're typing that in correctly, and you should get h equaling to 94.23 meters. This is. So we get our height being, to solve to the nearest meter, we do need to round that. So your therefore statement should be therefore the height of the cliff is 94 meters, rounded to the nearest meter. Okay, question 1 done. That's solving two triangles in 3 dimensions. We're going to do a couple 3 triangle problems, and we'll eventually, 2 triangle problems, we'll eventually get to a 3 triangle problem. So example number 2, I've drawn a diagram here already, and saying that John is 1.4 meters tall. So we've got John being 1.4 meters tall, and he's standing 12 meters away. So this distance right here, 12 meters, I've labeled it in red up there, from a building. So we can see here's a wonderful picture of my building. And the view from the top to the bottom of the building is separated by 55 degrees. So this full angle measurement is 55 degrees. I've kind of divvied it up into theta 1 and theta 2 because I'm going to divvy that 55 degrees up into 2 different angles, but the full thing is 55 degrees. I want 2 different angles because I saw I could make 2 right triangles here and make this problem a little easier. How tall is the building to the nearest tenth of a meter? So I want to look at this bottom triangle first. I'm going to highlight this bottom triangle. Let's go purple here. So from John to the building and straight down, all buildings in math problems are 90 degrees to the ground. And we see that line of sight is parallel to the ground. So we've got a right angle triangle here that has 12, 1.4, and an unknown theta 1. So to solve for theta 1, or that first angle here, we can use SOHCAHTOA. So we have to think, what if this is the opposite over here? 1.4 is the op, and 12 is the adjacent in this case. What trig ratio uses opposite and adjacent? That'd be tan. So we can say that tan of theta 1 is equal to op, which is 1.4, divided by 12. If we're solving for an unknown angle here, we have to use the inverse function. So that would be the tangent inverse of 1.4 over 12 to solve for that missing angle. And we get the answer of, when we throw this into your calculator, 6.7 degrees. Theta 1 is equal to 6.7 degrees. Not very much. So then we take a look at theta 2. If this one is 6.7 and the full thing is 55, we can simply subtract the 2 to solve for theta 2. So theta 2 going to be 55 degrees minus theta 1, 55 minus 6.7 is equal to 48.3 degrees. So we've got theta 2 now. So now if we look at theta 2, we've got another right angled triangle. So we've got this right angled triangle from highlighter from John up to the top of the building, down to completely horizontal and across. So once again, another right angle triangle here. Then if we take a look at that right angle triangle and we say that x is the opposite, and once again 12 is the adjacent here, then we can solve for x. So to solve for x, we're going to use TOA again. That tan of 48.3 is equal to the opposite, which is x, divided by the adjacent, which is 12. So we can rearrange and solve for x. 12 times the tangent of 48.3 degrees is equal to x. And we get the answer of 13.46 meters. So x would be 13.46 meters. Now they wanted the full height of the building to the nearest meter. So we'd have to add x to 1.4. So the full height, therefore statement should be h is equal to 13.46 meters plus 1.4 meters, the height of John, is equal to 48 is equal to 14.86 meters. It wanted it rounded to the nearest tenth of a meter, so we are going to round that to 86. We're going to round that to 14.9 in our therefore statement. Therefore, the height is 14.9 meters. So slightly easier problem. While it didn't look like you could use SOHCAHTOA to start, we broke it up into two right angled triangles. Use SOHCAHTOA. Usually makes your life a little easier if you can make right angled triangles with enough information to solve. Sometimes you can try to make the right angled triangles, but it doesn't have enough information to solve. Looking up, example number 3, looking up the top of a distant mountain, you measure the angle of elevation, 24 degrees. You then walk 35 meters closer to the mountain, and you see angle to be 32 degrees. How tall is the mountain? Okay, so let's draw us and some flat ground to start with. Now I'm not going to draw the edge of the mountain, I'm just going to draw the peak of the mountain. So this is the peak of the mountain, and I want to measure the height of that mountain. Why this mountain probably does something like this. I'm not too worried about that hypotenuse measurement. I want to know the height, remembering that height hits the flat ground at 90 degrees. So that's the peak of the mountain up there. So our first line of sight, you measure angle of elevation to 24 degrees. Maybe I drew this not quite to scale, but that's okay. 24 degrees. You then walk 35 meters closer to the mountain, measure the angle of elevation, so from the ground up, to be 32 degrees. So we're going to walk up here. Looks like my scale is going to be a little off, but that's okay. And we measure this angle to be 32 degrees. And of course, this measurement down below from here to here is 35 meters. And now it wants to know, how tall is the mountain? How tall is that mountain there? So a couple things we can figure out relatively quickly is that extra angle right here. Let's do purple. This extra angle here, we can call that, let's give everything a name here, A, B, C, and G, just so we know what we're talking about. So we can find the obtuse angle at B. So that angle B is going to be in triangle ABD, I guess it is. Triangle ABD. We can figure out angle B to be 148 degrees, so angle B equal to 148. I'll draw that right in there. 148. And then angle D way up here. This tall, skinny one. Hopefully it works out to be pretty small. 148. 180 minus 148. Minus 24. Equaling to 8 degrees there, do you believe? So we've got this small angle up here in the top. So these two triangles, ABD and BCD, they share something in common. They share side length DB in common. So if they share side length DB in common, then we can solve for that and use that in triangle BDC. So I think there might be more than one way to solve this, but this way will work for now. So we want to solve for this unknown side length right here, DB, because it is common in both triangles. So I'm going to use sine law. So in triangle ABD, I can say that, well, sine of, I've got a complete ratio, sine of 8 over 35 is my complete ratio. So then I'm going to say, compare it to this ratio of sine A over A. So in triangle ABD, let's go A over sine A is equal to D over sine D. Would be my ratio. And fill in the values we know. 35 over sine 8 is equal to A over sine A. Oh, I wrote this backwards, that's okay. A over sine 24, making that terrible looking A. Multiplying both sides by sine 24, we get 35 times sine of 24 degrees divided by sine of 8 degrees is equal to A. And throw that into our calculator, and we get 102.29 meters. So we've solved for our common side. So this side is going to be 102.29 meters. So then we can take a look at that second triangle. So in, let's say orange, I take a look at triangle BCD. And that's just a small right angled triangle. And we have, from theta, we have the opposite, and we have the height. So what trig ratio uses O and H, that'd be sine. So the sine of 32 degrees is equal to H, the opposite, divided by the hypotenuse, 102.29. Times both sides by the denominator, 102.29 times the sine 32 degrees is equal to h, and we get h being 54.2 meters. Let's double check that with my calculator here. 102.29 times sine of 32. And I get 54.205 or 54.2. Did do that one right. And a 0 in there to show we rounded it. So we have the height of the cliff, or the height of the mountain, to be 54 meters high. Not a very tall mountain. So once again, we're using a bit of sine law, a bit of SOHCAHTOA in that one. There may have been another way to solve that using only SOHCAHTOA. I'd have to put some thought into that. Number 4, standing on a beach, you see a red boat at a beach, north 30 degrees east. So first thing we got to know, never enter smelly washrooms. Northeast, southwest. If you took geography class with me, you should know that. So let's draw, this is me, we are standing on a beach. Then at a bearing of north 30 degrees east. So the way we read that is north. So north is due straight up and down. We're saying north is straight up and down. And then from that north, we go 30 degrees to the east. So we go 30 degrees that way. And we see a red boat out here. I don't know how far out there. I'm just going to put a dot. We'll label the distances later. But we see a red boat at north 30 degrees east. Then next one, we have a blue boat at south 20 degrees east. So almost in the same fashion, you follow the first letter first, so south and then 20 degrees east. So south is straight down. And then from south we go 20 degrees east. That looks to be about 20 degrees, a little less than 30 degrees. And I don't know how far. I'll label my distances later, so clearly this is not to scale. And we see a blue boat at 20 degrees east. Now from the blue boat's perspective, the angle between you and the red boat is 28 degrees. So now we have to imagine we're at the blue boat. So from the blue boat's perspective, he looks around to us, to the other boats at 28 degrees. Is the difference between us two. So I can draw my third line of a triangle right there. So quite often setting this diagram up is the most challenging part. Once we have the triangle drawn, the math behind it's not too bad. Then the distance between the two boats is 3 kilometers more than the distance between you and the blue boat. We don't know the distance between us and the blue boat, so I'm going to call that x, and then the distance between the blue boat is 3 kilometers more. So x plus 3, now knowing that x is measured in kilometers. That's all the information that was given. Of course, we can do a bit of extra calculation. We can say, okay, well, we know from north to south is 180 degrees, so if you take off 30, it's 150, take off another 20, this angle measurement must be 130 degrees. Well, if that angle measurement is 130 degrees, then we know the 3 angles in the triangle, so angle R must be equal to 180 minus 130, 50 minus 28, leaving us with 22 degrees. So they do give us a bit of extra information with some quick math. Then we're looking for side length x. So I'm thinking, okay, here's my ratio, complete ratio of me and side me to R inside R. So I'm going to use sine law. So let's say our unknown is x. I'm going to put that on the numerator. X over the sine of the angle opposite to x, or sine R in this case, is equal to, this is solving for x here, our other ratio of x plus 3. It's a funny looking complete ratio, but notice we only have one variable. It's just the x that is unknown, so we can solve for one variable. It's going to be a bit of extra work. We're going to have to distribute. That's sine attached to x plus 3, then bring the x out inside, factor the x out and divide. Of course, you could type this into your calculator halfway through and get a rounded answer. It'll still be pretty exact if you keep 3 or 4 decimal places, but good habit to get into is solving this without rounding mid-question. Try to save all your rounding to the very end. So I'm going to multiply the denominator by both sides, get them out of the denominator. Then if you're an arrows man, you can draw in your arrows here. Distribute sine 22 into those brackets. Nothing happens on the left-hand side. Keep that as is. X times sine 22 plus 3 times sine 22. Now I've got two variables. I've got an x here and an x over here. So we want to get those x's together and factor them out, so we only have one x in this equation. So x times sine 130, when I bring this over, it becomes negative, times x times sine 22 is equal to 3 times sine 22. I've got my two x's, so I'm going to factor an x out of both of these terms. Quite the opposite of distributing that sine 22. Now I'm going to factor an x out. When I factor an x out, it's going to be x times whatever is left over when I divide both terms by x. Sine of 130 minus sine of 22 is equal to 3 times sine 22. Then I'm going to divide both sides by the brackets to isolate the x. To get x all by itself, we only have one x. Now we can just simply throw that into our calculator. And we are rounding to, doesn't say, so we can keep 2 decimal places there. 3 times sine 22 divided by sine 130 minus sine 22. Let's say you're making a mistake. Make sure that denominator is in brackets. If denominator is not in brackets, it may do the first calculation and then subtract sine 22 from everything. So make sure that's in brackets, and we should get the answer of 2.87 kilometers. So your therefore statement being you are 2.87 kilometers away from the blue boat. Therefore, the blue boat and red boat would be 5.87 kilometers away from each other. So kind of setting up that diagram is the more challenging part. The math after that is sine law. You've done that type of sine law where you have a variable on each side and have to get them together. Some of you multiplied it out, so you actually got the decimal for sine 130, 0.7 something. You actually got the decimal for sine 22, and then you just subtracted the two. That will work. I prefer to keep it a little more accurate and do your distribution and factoring there. Okay, second last one. No, last one. You're standing in front of a building, example 5, directly in front of you at an angle of elevation of 65 degrees. So this is probably one of our more challenging problems. So let's draw our building here. And straight ground. Building hit the ground at 90 degrees. And we're standing directly in front of it. So I'm going to draw a straight line there, 65 degrees to the top of it. Juliet is on a balcony on the 3rd floor, 9.3 meters up. So not to the top, just to the 3rd floor, 9.3 meters up. And then Romeo is standing directly to your right. So this is where the instructions are a little challenging if you haven't done these problems before. So directly to your right introduces kind of a three-dimension to this problem. So directly to my right, I'm going to say if we're facing the balcony, we're facing that building. Directly to my right would be something like that. Now this is kind of introduced our third dimension where it's going to get a little trickier. Romeo is standing to your right at a distance of 5 meters. So he's 5 meters away from us. Excuse me. At what angle must Juliet look down on Romeo? Angle of depression. So we're looking from Juliet is going to look down to Romeo over there. I'm going to complete this off. Imagine you're standing where Romeo is while it's on a different plane. It was hard to read there. His line of vision still hits that building at 90 degrees. So there'd be another 90-degree angle in there. So we've got a couple different triangles. I'm going to draw Juliet. I'm going to draw me. I'm going to draw Romeo. I'm going to draw the base of the building. So we're going to have to take a look at a couple different triangles here. See what we can solve for. So first one, let's go the easiest one here. MJD, me, Juliet, and the base. BJ, me. Let's do this one green as well. So the first one we're going to solve for here, we've got a 65-degree angle, 9.3 height, and a 90-degree angle. So we want to solve for something that is in common, because eventually we want to figure out that angle of depression, so from Juliet looking horizontal downwards. So we want to find for something that is common in another triangle. Notice how triangle MRB shares in common this MB length. So if I solve for length J, or side length MB, I have a piece of the puzzle that'll work in my next triangle. So I'm going to solve for length J here. So knowing what I know here, I can say, well, this is my opposite over here. This is my adjacent. So I'm going to say that the tan, opposite and adjacent, the tan of 65 degrees is equal to my opposite, which is 9.3, divided by my adjacent, which is J. We can do this in one step. You guys are probably getting good at this now. Multiply J by both sides, so you get J times tan 65 is equal to 9.3. Then divide tan 65 by both sides, so we get J is equal to 9.5 divided by tan 65. And we should get J is equal to 4.337 in this case. I'm going to keep an extra one just because it's very early. The calculations are going to try to be a little more accurate. Is side length J. Notice that this is also side length. I'm going to call this BM, just because there is no J in the next triangle, so let's call it BM. So then if I take a look at this next triangle, let's say this orange triangle, so you could picture it here. So triangle MBR. Has a right angle in it as well, right there. We know this distance is 5. We just figured out this distance is 4.337. This is B, this is R, this is M. And then we think, what is common between this triangle and the next triangle we're going to look at, the next triangle being RJB. that would be side length M over here, or side length RB. So if we solve for that length, then we can use it in our third triangle. So let's solve for that length. We don't have either of those angles in here, but we do have two sides, neither of them being the hypotenuse. So we can say Pythagorean theorem, clearly m squared is equal to r squared plus b squared, or two side lengths squared, square root it. So m is going to be equal to the square root of r squared is 4.337 squared plus 5 squared, 25. And we get m is equal to 43.0809. Take the square root of that, and we get 6.619 meters. Is that side length m, or is that side length also called BR? Just because there's no m in the next triangle we're going to look at, that blue triangle. So now we take a look at our last one here, from Juliet down to the base of the tower, out to Romeo, and back up. That is another right angle triangle. It's kind of hard to picture that one because I'm trying to draw it 3D coming out of the page a little there. But if I draw that same triangle here in 2 dimensions, so it's a little easier to see that 90-degree angle. Might look something like that. Where we've got Romeo, Juliet in the base. Of course, that tower is hitting at 90 degrees. We are on flat ground. She is 9.3 meters high. We just solved for RB. RB is 6.619 meters. And the question is asking for the angle of depression. So the angle of depression that Juliet is looking down, remember the definition of angle of depression is from the horizontal downwards. So if that is the horizontal line, the question actually wants from this line down here. Now we know that the horizontal, that must be parallel to the ground. So this angle right here, we'll call this theta 1, must be the same as theta 1. So we could solve for that angle in the triangle, or we could solve for this angle right here, theta 2, and simply do 90 minus. And that's a common mistake, not knowing the definition of angle of depression. A lot of people confuse that question. They think they're actually asking for angle 2, or theta 2 there, but angle of depression measures from the horizontal downwards. So it must be theta 1 there. So if we are looking for this angle theta 1, it's the same here due to the Z pattern. We can say that this must be the opposite. This must be the adjacent. So tan of theta 1 is equal to the opposite, 9.3 divided by 6.619. Since you're trying to solve for an angle measurement, you need to take the inverse of that function to isolate for theta. So we've got the tangent inverse of 9.3 divided by 6.619. And we should get the answer of approximately 54.6 degrees. That would mean this is 54.6 degrees. That's due to our Z pattern. This is also 54.6 degrees. So Juliet is looking down at an angle of 54.6 degrees, angle of depression towards Romeo. There's a longer question. You need 3 triangles to get all the way over to solve for that angle of depression. The math behind it is not overly challenging, just using SOHCAHTOA and Pythagorean theorem, but definitely setting that diagram up and making sense of all your angle measurements is the challenging part there. Our next lesson, obtuse angles in a triangle, we are not going to do. So can skip that lesson, put a big X through that one. If you want to go ahead and look at it, Google it. It is very interesting. If not, we'll learn about it